Welcome back, everybody. For the last section, we're going to talk about absolute age. So to help with wrapping our minds around just how old the Earth is, we're going to do a little exercise here, right? You imagine you're put in some alternate world where a year passes with every single second. So each second that goes by is a year, in which case you could go through 100 years of time in about a minute and 40 seconds. It's about 100 seconds. 1,000 years would take you about 16 minutes, 40 seconds to go through. You could go through 10,000 years in about one full class period, 2.5, 3 hours. You can go through 100,000 years in about a day, a little more than a day. And you could go through 300,000 years, which is about the total amount of time that modern human beings have been on the planet, Homo sapiens. That would take you about 3 days and 11 hours. But the Earth is much older than 300,000 years old, right? You could get to 1,000,000 years, and it would take you about 11.5 days here, almost 2 weeks. To get through 1,000,000,000 years would take you 31 years, right? Even in this alternate universe where a year passes every second, it would still take you 30 years to get through just a piece of Earth's history. And to get through the entire age of the Earth here, let's move me out of the way, it would take you 144 years. So about 2 human lifetimes in the box where a year passes every second to get to the age of the Earth. That is how old it is. It might also help to look at this visually, right? So this is maybe $10,000 here, right? That's about how much 10,000 is. Have about $1 million worth of cash here. And then there's this big jump from $1 million up to $1 billion worth of cash. So when we talk about the difference between 10,000 years, right? About the time period of the Ice Age versus 1,000,000 years. So before the Ice Age, but when you still have a modern Earth with modern animal and plant life, all the way back to 1 billion years ago, back before animal life really existed. That is the sort of orders of magnitude that we're talking about. Our first question here, how old is the Earth, and how does anybody know how old the Earth is? So the Earth is 4.54 billion years old, and here's how we know that. So the question of how old the Earth is, moving back for a step, is a long-standing question, right? Every person who ever lived would wonder, well, just how old is this thing that we're all living on? If we go back to Halley, famous Halley's Comet, he suggested calculating the age of the Earth based on the rate of salt accumulation in the sea. Charles Darwin proposed that based on the rates of evolution and diversity of modern life, you could get a figure of about 300 million years. Kelvin, same, temperature, Kelvin, same guy, he used his ideas about physics to estimate the age of the Earth, got a figure of about 20 million years. John Jolly, a scientist who calculated the approach that Halley had put forth, talking about the amount of sea in the oceans, how long it would take, and got about 90 million years as the figure. But it wasn't until radiometric dating that any sort of a reliable estimate for the age of the Earth could have been found. And actually, if you notice, everything over here, these are all lowball estimates. The Earth is far older than anybody had actually predicted up until the discovery of radiometric dating. So what are we talking about here with radiometric dating? Some atoms are unstable. They are radioactive. For example, uranium is commonly found in granite rocks. And eventually, over long periods of time, because it is unstable, it changes into another element. It actually changes into lead. So the uranium here we would call the parent. And then over time, slowly, the parent changes into the daughter, which is lead. So with that in mind, what does it mean to do radiometric dating? Well, the process is a comparison. You are comparing the amount of parent, which is uranium, to the amount of daughter. And over time, because of the decay process, you'll get more and more and more of the daughter. So then if you look at the ratio of parent to daughter, you can tell about how long the decay process has been taking place, and that tells you how old the rock is that you're looking at. So here's another way to sort of visualize this, right? We start off, we're at time 0. The rock has just formed, just gotten cool enough to sort of lock things in. The clock starts ticking. We're at 0 half-lives. We'll talk about what that word means in a bit. Everything is a parent. So a certain amount of time goes by, and we're going to call that certain amount of time the half-life. And after one half-life, half of the atoms of the isotopes are parent, and half of them are daughter. So we're going through the decay process as we move to the right here. And then we have 0 times 0, rock first forms. We have 1 half-life. Now it's 50-50 between parent and daughter. And let's say we go further in time, we repeat that same amount of time again. Well, now 2 half-lives have passed. So if somebody looks at the rock and analyzes what is going on inside of it, they would see this. They would see that we are at about 75% daughter and about 25% parent. So then somebody could look at the rock, analyze it with this, find the ratio, and then using known information about the half-life, they would be able to tell you the age of the rock. So to wrap it all up, radiometric dating is the process used for numerical age determinations of rocks on Earth and other things too. It involves a comparison of the relative amounts of daughter isotope, the new stuff, to parent isotope, which is the old stuff. Now, if you look at the chart over here on the right, you will see there are many different parent-daughter combinations that can be used for radiometric dating. Some which have half-lives that are absolutely enormous, 50 billion years or so, older than the age of the universe, and some which have half-lives that are a little bit smaller, even as little as about 500 million years. And it's actually this, uranium-235, this specific uranium isotope, this specific type of uranium, that was used to estimate the age of the Earth. But there's also this question that I've been avoiding so far, right? You say, okay, you can date old rocks to find the age of the Earth, but how do you know where the oldest rocks are? Like, where can you find the oldest rocks so that you can then apply this numerical process and find an absolute age for the Earth? Where do you find them? Well, it's very rare to find really, really old rocks on Earth. There are all these processes, plate tectonics, weathering, erosion, recycling of materials. It just makes it really, really unlikely for whatever rocks were there when the Earth was formed to make it to the present day. And in fact, it's not believed that this has happened. It's believed that the oldest rocks on Earth are at about 4.03 billion years old. So a full 500 million years after the formation of the Earth. Next time you're in northern Canada, you might check out the Acasta gneiss. And this reminds me, the final number in the Axis code is 4. Okay, so those are the oldest rocks on Earth, and they are nowhere near old enough. But the oldest rocks, that's different from the oldest minerals, and we'll talk about why in the next unit. But the oldest minerals are these things called zircons, that look like this, and the oldest Earth materials are in these minerals called zircons in sandstones found in the Jack Hills of Western Australia. These can be dated radiometrically, found to be about 4.36 billion years old, but that's still not old enough. Okay, so what if we don't look at Earth? We actually look at rocks on the moon. Well, there's no plate tectonics on the moon, there's no weathering or erosion or recycling, anything else that would get rid of the rocks on there, right? So we should have old rocks on the moon, and in fact we do have old rocks on the moon, older than anything found on Earth, something in the neighborhood of 4.4 to 4.5 billion years old. But still this is not old enough. Well, in order to find rocks old enough, we actually have to look to space. So meteorites in the solar system are believed to contain the same original sort of primordial material which is there originally in the formation of the solar system. So about 50,000 years ago, one of these hits Earth, creates a meteor crater. Later in the 1950s, much later in the 1950s, a person named Claire Patterson came along and actually did this radiometric dating process that we've been talking about on rocks from meteor crater. And this is finally how we get 4.54 billion years old. A surprisingly accurate estimate for the age of the Earth, considering how long ago it was that this happened. So our final answer here for the age of the Earth and the solar system is about 4.54 billion years. And you see, right, plus or minus 50 million here. This is about the approximation for how long it would have taken for the solar system to gradually evolve. And we've made it. Now, by comparison, the Milky Way galaxy is about 13.2 billion years old, about 3 times as old, and the entire universe is about 13.8 billion years old. So much older. Well, let's ask another question now. Where are the oldest rocks in Arizona? So, oldest rocks are going to be at what is essentially the bottom of the Grand Canyon. It's going to be about 1.75 billion years old. There's something called the Vishnu supergroup down there, basement rocks in the Grand Canyon, and if you look, there's something called the Brahma schist. something that is about 1.75 billion years old, found here. There are also rocks which are almost this old all around Arizona, including some in the White Tank Mountains. So that is everything in Unit 4. What are the big ideas here? 3 ways to date rocks, right? You have absolute age, relative age, geologic age. You want the 6 principles of stratigraphy. I want to know the types of unconformities and what they mean, what the geometry looks like, how to explain them. And I want to know about the absolute age of the Earth, as well as the evidence and the process of figuring out the age of the Earth. That is all I have for you. For those of you who have made it to the end, thank you.